Hello, welcome to Everything Distributed. Today we are going to talk about proof of work, but with the focus on the attack. And the content is again based on the Bitcoin and cryptocurrency technology and then Bitcoin white paper. Last time we talked about like Bitcoin, it has this kind of a one-run consensus protocol design. And then the key is proof of work, where you do the mining or you search the puzzle. And then the key is that once some miner found the block, then it propagate to everyone, and the block will be accepted and be appended to the chain only if all the transactions are valid. And this is one of the key design such that to ensure that the transaction or the transaction inside the block is valid. And by valid, at least in the context of cryptocurrency, is that the buyer actually has enough balance, and then the signature of the transaction is actually correct. Now let's look at like more detail on the consensus protocol. And then the key, right, is that to ensure the ordering of block is the same, and then it needs to ensure that everyone has the same chain of block. So in this case, only one miner like finds out the content of the block for this slot, then everyone has the same blockchain. So that's good. But it's possible that because all of this kind of puzzle solving or the mining is randomized, so it's possible that two miners, they find out the block roughly at the same time. And in this case, we might have disagreement. And if we have disagreement on the blocks of the chains, then the double spending attack is possible. So for example, in a red block, maybe it contains a transaction, say that Louis pays Starbucks with $10, and green block stating that, okay, Louis uses the same $10 to pay Amazon. Suppose I got lucky, then actually I got my coffee and then I got my package from Amazon because they check the different blockchain and say, okay, Louis transaction is actually valid. And that's the important thing about proof of work or any kind of this kind of consensus-based blockchain. You need to ensure that everyone has the same blockchain. Then one idea behind this proof of work and why you need to adjust the difficulty is that during a period of time, you only want to have one block to be found. So to avoid this kind of attack. And again, it's a probabilistic, so you can only ensure that I achieve this in a high probability. And in general, like what affects the difficulty is the computation power, how fast each miner can solve this like proof of work search puzzle. And then the other factor is some message delay. Because if the block is very large, I think right now it's a few megabytes, it really takes time to propagate to everyone. So that's also something needs to be considered on how to set up your difficulty. And now let's look at the effect of asynchrony. So suppose that the block, like you adjust some difficulty, but somehow this miner got lucky. It got like 2 consecutive blocks. And now this like the bottom miner is not lucky, and then the message delay is very long, so it doesn't receive any of the red block or green block. So it's working on some stale blockchain. Then in this case, like what's the design that allow miners that converge to the same blockchain? And there are many different designs, and one of the most popular, and I believe it's the one used by Bitcoin right now, is the longest chain. So this bottom miner, when it receives the update from the top miner, you will see that, oh, this top miner already has 4 blocks, but I only had 2 blocks. So I should switch to the longer chain. And then that's each miner actually will use longest chain to decide like what is the current block that he or she should work on. But now, so now with like this longest chain, again, the double spending is possible because of this behavior of switching chains. So now let's look at this cases. This case, we have two miners, and one miner sees that this block said Louis pay $10 to Amazon, and then the bottom miner said, okay, Louis pay $10 to Starbucks. And suppose Starbucks check, oh, okay, you already include this transaction, that's good. I'll give Louis his coffee. But then because of the longest chain, this bottom miner say, oh, wait, I need to actually switch to the other chain. Then now it's that Louis pays $10 to Amazon. Then Amazon will give my package. So now I have both things. But why is this bad? This is because that the original block, which states that Louis pays $10 to Starbucks, actually is missing. It's an orphan block. No one will adopt it because it's not the longest blockchain. Well, what's the issue? Louis already drank the coffee, and Starbucks lost money. And this is the thing that we want to prevent from. And the design is that you need to have confirmation to make sure that, okay, actually that this block will not disappear. So remember that when I describe the scenario to you is that, okay, whenever Amazon sees that, oh, Louis, the transaction from Louis is included in the current blockchain, then I should send a package to him. But actually that if you need to have to stop from the double spending, then that's not the case. Amazon shouldn't send me the package at this point. It should wait until the blockchain becomes longer, that there are other blocks that's appended to this green block, and at least times of false confirmation is 2, then you can wait, Amazon can send me the package. And that's how the confirmation work. And in general, is that the more blocks you are waiting for, like the blocks after this green block, then it's more certainly that this green block will never be overwritten, because that's how the longest chain works. Now let's look at more detail why this longest chain plus confirmation work, and then this is in fact the original analysis in the Bitcoin white paper. So now suppose that, okay, I have a longer chain. It's actually Louis pay $10 to Starbucks and Louis pay Amazon is the shorter chain. Then the probability that we are looking at, the probability that no double spending is allowed, or that this orphan block, is that what's the probability that some miner will switch to a bad chain? Okay, what that means is that maybe that the other miner got lucky that the top chain grows much longer, and then this miner will switch chain, and then this Louis pays to Starbucks transaction, the block got missed, and then this is the bad probability that we should try to avoid. So the framework to analyze the probability is that first, you consider 2 types of nodes or 2 types of miner. It's honest node, meaning that it's a correct person, it's a correct miner, it follows a protocol. And you also have a taker, you can think of it as a Byzantine miner. He or she could do the arbitrary thing. And then the key is compare this probability. And then I remember what's the probability? It's related to the computation power. So you have P, the probability that some good node will find a good block, and Q is that attacker will find a block that's appending to the top chain. And then the final probability that we care about is that probability that attacker will ever catch up from Z block behind. And in this case, Z is 2 because the chain we want to stay on is 2 blocks longer than the previous block. And then this Z is the confirmation block that I mentioned. And if you follow the analysis in the Bitcoin white paper, if the P is that smaller than or less than Q, meaning that attacker is more powerful, then this QZ is 1. Because with overwhelming probability, the top chain will grow much faster. And then this is the part when we talk about 51% attack. So why 51? So if like Q equals to 51, then this equation holds. So the double spending attack can happen deterministically. But now let's consider other case. The good guys has more computation power. So I have P strictly greater than Q. Then in this case, if you do some mathematical analysis, the probability of the double spending attack by switching chains is Q over P to the power of Z. So it depends on the proportion of computation power between good guys and bad guys, and also the number of confirmation that you have. So here is an illustration. Suppose Z equal to 1. So the good chance that you want to stay on is only 1 block more than the bad chain that attacker tries to work on. Then what's the probability that attacker got both of the next 2 blocks? It's a Q to the power of square, Q squared. So in this case, the miner will change to the top chain and then attack is successful. But of course, that this is just one case. You also need to analyze the case that, okay, maybe attacker got 1 block, but the second block is gotten by the good person, and then so on and so forth. And then the math analysis is called gambler's run problem, which that we will not cover today. But then idea is that 3 things is Q and P and Z. Of course, that's only a very simple analysis on like whether double spending is possible by switching chains, but in real world, there are much more complicated factors, many more complicated factors. For example, you have network quality, asynchrony, whether every on this node is working on the same thing, and then you have a Byzantine attack. Maybe I can hold on the chains and I don't tell anyone, I just keep mining. And then there's also this eclipse attack, which is related to some kind of denial service attack. And then you also have game theory. You need to analyze what happened if some miner, they are selfish, and if like some miner cooperate with others. And yeah, so it's complicated and it's beyond the scope, but I just want you to be aware that Bitcoin was a very cool protocol, but in order to prove that what is the attack probability actually is very non-trivial. Okay, that's all I want to share today. Like we talk about longest chain, and then we talk about why we need confirmation, and in particularly like what do we mean by double spending attack in this context. That's all. Thank you.